we wrote an action out of thin air, which presumably is based upon some microscopic symmetries that we're interested in the whatever many-body system. It's a d+1 dimensional integral, which captures the quantum mechanics. The Berry space has been integrated over, and interactions have been included from a 5-4 term. Okay. So we've been labeling the coordinates, these d-dimensional coordinates, just by a label r. So this is like an integral over r. And for every different, for every, I guess, set of coordinates, it's these sort of indices which come into play in the internal vertices of the diagrams. This piece, including the integral, is the Gaussian part of the action, S0. And that's important because it's the Gaussian weights that we essentially know how to integrate over. We know how to do Gaussian integrals. And the part that we don't know how to handle is the 5-4 piece, which is the interacting part of the action. Okay? So we did a free energy calculation, which illustrated sort of this cancellation of certain diagrams. We're going to talk more about that. And what we ended up calculating last time was the expectation value for two fields, one at position R1 and one at position R2. And this thing is, it's like the Gaussian expectation value of those fields weighted by the interacting part of the action, which depends on all the fields. That subscript means that there's a Gaussian weight in this expectation value. And in the denominator, I just don't have the fields. Okay, and that's the thing that we've Taylor expanded. Okay, numerator and denominator. And so once it's expanded, you have different orders. So in principle, you should take this up to infinity. But good luck. Okay, so it's this thing. I've Taylor expanded the exponential. So minus SI, which depends on phi to the k. Gaussian expectation. Good. And the reason we do this is it sets us up to use Wick's theorem on every term of this Taylor expansion, right? Because what this is just the integral over that 5-4 with some constants. Okay, so we have this sort of internal integral, and then we just have fields at that coordinate system, so we call them phi at r. So we have things that are like phi r1, phi r2, and then say, phi 4, all depending on r. That would be the k equals 1 term. And if k equals 2, then we square that term. So we have two integrals over r, and we've squared the phi 4 term. And so then each one of those is set up to evaluate with Wick's theorem. So for example, every one of these terms has, I think I labeled them with i's. Depending on what order you go to in the expansion, in the Taylor expansion, you can have all sorts of different numbers of fields in this expectation value. And what we're doing is we're summing over all pairings. So all possible pairings of the indices. That's where these diagrams come from. Written in terms of, I guess, the elementary, if you will, 2-point Green's function here. So you write all these endpoint correlators that occur in this expansion. And it's just a product of all these G's. And these indices are, instead of discrete variables, I mean, we're using R1, R2, and the various R that come in to all these powers, right, from this integral here. Okay, so last time we wrote the 2-point correlation function. It's just a numerator and denominator. Just this numerator and denominator. And we looked at all these terms separately. For example, in the numerator, okay, so for k equals 0, you'll get just the Gaussian 2-point correlation function is the first term. That's the k equals 0 term. So the 0th order approximation to the fully interacting, if you will, 2-point correlation function is just that same two fields evaluated with a Gaussian expectation value. Okay, makes sense. So if you're doing a perturbation theory in sort of U, in the strength of the interaction, that makes sense if that's your first term. The second term is k equals 1. So it's 1 power of SI, if you will. So it's 1 power of the 5-4 term. And then the next term in the expansion would be the k equals 2 term. So you have two integrals of 5-4 with a Gaussian expectation. Plus higher order terms. And last time we ended up evaluating this thing to first order in k, if you want to call it that. So remember, this is k equals 0. This is k equals 1. This is k equals 2. So what do we get? We got we only got two graphs that survive. One is from the sort of 0th order term, and one is the connected graph from the k equals 1 term. And we argued that all of these disconnected graphs canceled when you expanded the denominator. Okay. So I ended by just saying that this corresponds to some theorem, but let's look a little bit more closely at exactly what graphs, I guess, cancel. And it becomes a little more obvious when we go to one higher order. So this term, right, came from the k equals 1 term in the expansion. So now let's look at the k equal 2 term. So it has coefficient 1/2 u over 4 factorial squared. And again, if u is small, then that term's getting smaller and smaller as you go to higher and higher orders. Okay, so let's just look at the diagrams that would occur in the numerator. Okay, so I've written the expression explicitly right there. So you basically have indices. So you have something, I'll draw it like this. So R1, you have the phi-4 term at R. You have the phi-4 term at R prime. And then you have the other field that you're calculating the correlation function for at R2. So to perform perturbation theory, you have to find all possible ways of connecting all these vertices. And again, remember what this is basically just calculating all the pairings that are occurring in this sum. So it's just a graphical notation for doing Wick's theorem, right? So there's all sorts of crazy ways to do this. So for example, you could connect, let's do the vacuum graphs first. So you can imagine connecting the two external fields, and then just connecting these in all possible ways like that. And we've already done stuff like that before. So there's one possible way to connect the external fields. I think there's 3 each for those, right? So it should be 3 times 3. So this will give you 9 graphs like that have a topology like that. That's just one possible way. Then you can imagine connecting R1 to R2, but then connecting these internal vertices together somehow. And this type of combinatorical thing, we've also already calculated before. So let me start drawing these all out. So to get 9 of those things, these ones here, I just wrote down the combinatorial factors. This one's 72. You can also imagine just connecting, instead of looping these ones on the outside, you can imagine connecting them through here. I'm just making a big mess. But that would also give me a disconnected graph that looks like that. And I think we already calculated that combinatorial factor. That's 24 in front of this one. And you got to get all those right. You got to get all these numbers right, or else your perturbation theory will give you the wrong answer. Just so these are in your notes, so that when you teach it someday, you don't have to recalculate them. 72 of these ones, where I've calculated, where I've connected R1 and R2 to just one single vertex and left one floating. Say this is R and this is R prime, if you want. Okay, and now there's 3 graphs where I've connected everything together. Okay, so that's R1, that's R2, and sorry, that's R and R prime, and I've connected one of them to R1 and R2. Happens to have a combinatorial factor of 288 for some reason. 1, 2, 3, 4. You can also do this. And the last one is something like this. Okay, so you'd calculate the numerator, and then you would calculate the denominator. And we've already essentially done this to this order. I think when we calculated the free energy. So this includes, actually I've included all the contributions. This is only the contribution up to u squared. This is only for the u squared term. And this is the k equals 0. So this one is the u term, I think. Yeah, and these are all the u squared terms here. Okay, so you have to add all the terms in the numerator and all the terms in the denominator. So if we keep track of the signs, and we kept track of all the combinatorial factors, so let me just absorb all these combinatorial factors and everything into the diagrams. Let's see if I can do this all on one chalkboard. Okay, this is the Gaussian piece from the numerator. I'll keep track of the signs, but not the combinatorial factors. That's the order u term. I haven't canceled anything yet. This is 1/2. That's this 1/2. Then I have the u squared and the combinatorial factors. So you get 4 of these things that are disconnected. And you get 3, so that's the first 4 here. 1, 2, 3, 4. Then you get 3 that are connecting all the vertices together. Okay, that's the order u squared term. And on the bottom, one, 2, 3, 4. That's everything up to order u squared. So again, then the game is you expand the denominator, treating this as epsilon. One, it's got to be minus, right? 1 minus epsilon. Then just like it, you would find, just like it did for the order k equals 1 terms, which are the order u terms, then a bunch of graphs cancel, and you can almost see it from here, but you're basically going to cancel things that are like, this multiplied by, this term here, which gives you this one, right? Same with this one, same with this one. So this one is a combination of this one and this one, and so on. And so the graphs that cancel will be those type of ones where you have what I'll call an internal vertex, which is one of these R or R prime vertices that just floats around. So it's like, anytime you have something like this, is there an internal vertex floating there? That's both of them floating around. This one. Those are the graphs that cancel. We call those things vacuum graphs. So what a vacuum graph is, or a vacuum diagram, contains one of these floating interaction vertices. One of the vertices corresponding to the actual SI, or the phi-4 term. Okay, so if you're not connecting to these points here, if one of your vertices that comes from the interaction doesn't connect to those points, then that's a vacuum graph. So that's the link cluster theorem that I mentioned last time. So I forget if I wrote it. So instead of worrying about connected, what we define as a connected correlation function, which I might have said last time, I want to define what we mean by a vacuum graph. That's this definition here. So the link cluster theorem is in that ratio of the perturbation theory of any correlation function all vacuum graphs cancel up to any order in U. And you just keep writing that type of equation out to higher and higher orders with all the proper combinatorial factors and all the minus signs taken care of. And you'll see that all of these numbers that you're seeing here are canceling and so on. So once you know this, then you basically don't have to worry about the vacuum graphs. And you don't have to calculate the denominator at all. You just calculate all the fully connected graphs in the numerator. Oh, sum of all graphs excluding vacuum graphs. So no need to calculate the denominator. Just believe the link cluster theorem. Okay, so that's fine for the 2-point correlation function. But like we started discussing last time, what if you have a higher order correlation function? You have different connections between the R1, R2, R3, however many R's you have. Okay, so just let me take a quick look at a 4-point correlator. I'll just write down the graphs that contribute and the ones that don't. And you'll see if we define vacuum graph in this way, then everything should be fine. Okay, so just a quick sloppy example. I'm not going to do the whole thing. By the way, a lot of things I read on the board you might have to search around to find in books, but I think these perturbation theories are completely standard. You can find them in any of the recommended texts for this class. The 4-point correlation function, I don't know. Maybe. Why you want to calculate this thing is another question. But just imagine I've 4 different positions for my fields. I have this field theory. I have these fields that live in D plus 1 dimensional space somehow. And I want to know how 4 points in that coordinate system, how the fields for 4 points are related. So nothing's affected when I do the first few steps of this. I'll still get the 4 fields. In a perturbation theory that comes from expanding the exponential associated with the sort of interacting part of the Hamiltonian. So the first order, or the 0th order in K, I guess. You just get the Gaussian expectation value of the 4 fields. But then the next term, first order in K, you have some integral over the 5-4 term. Okay, so let's not worry about the denominator. And imagine what we're going to do with the numerator. Because we believe the link-cluster theorem. So that first term, so I'll just do this graphically. You have to find ways to connect R1, R2, R3, R4. Okay, so you still need Wick's theorem. Right, you're writing this as a sum over all possible pairings of the indices. Okay? So you'll get something like this. I don't know. This. This. Yeah. So the next term, the U term, we somehow need the expectation value of, it's like R1, R2, R3, R4 with a field inside that has 4 lines coming out of it, say. Okay, so it looks a little different than what we've done for the higher order term in this case. Okay, so let's just examine this thing here. Okay, so that's going to give you, first off, you can do the simple thing where you connect R1, R2, R3, and R4 together, and then just make these, they're called butterfly graphs, I forget. Everything, all these things have names, but nerds have named these things. Like a penguin diagram, is that one? I don't even know what that is. So the first term for here will be just connecting these, it's like you have these 3 configurations here. And that center vertex, it's the 5, 4 vertex, just connected to itself in the, 3 possible ways. And that, by definition, is a vacuum graph. So if you did this full expansion, you would just say that that thing's equal to 0. But if you trust the link cluster theorem, just be like, I don't even have to worry about anything with this. Just set it equal to 0. Then you're left with diagrams that you have to add, right? That's only one contribution to Wick's theorem. Another simple one, you can imagine connecting R1 to one of these things. There's 4 possible ways to do that. Then there's 3 left to do R2, so it's 4 times 3, times 2 times 1. So you get something like 24. See, I do all the easy combinatorial ones. I don't know where that 288 comes from. So you have another thing that's like that. There's 24 graphs that look like that. That's not a vacuum graph. that interaction vertex, the phi 4 vertex, the one that's labeled R, is connected somehow to the R1, R2, R3, R4. Okay, so then you can imagine connecting. Yeah, so what's different about this 4-point correlation function is you can imagine connecting two of these to them, not to the interaction vertex, and then two of these to the interaction vertex, right? Then you have to have an integration loop. So every time you do that, let's say I connect R3, R4. R1 connects to the center R, right? And there's 4 possible ways. Then there's 3 possible ways to connect R2. So every time you have one of these graphs, the combinatorial factor has got to be 12. But then there's different ways to do that. One, two, three, four. Let's see. Oh yeah, and I got to connect through the diagonal. And then the other diagonal. Something like that. So each one of those occurs 12 times. Are they vacuum graphs? Do they cancel? They're not, because the interaction vertex is connected. Okay, so those are the ones that you got to be a little bit careful about when you do these higher order correlation functions. If you have a really high order correlation function, you'll have a lot of these types of things, right? But in general, they're not vacuum graphs by this definition here. So they'll contribute. You have to be careful with how they occur. That's it. Writing this out, getting these factors straight, and then don't forget what you're calculating. Each one of these things, R1, R2, R3, R4, R corresponds to 24, should be minus u over 4 factorial, right? There's an integral over R. And then all of these, so it's going to be R1 minus R, R2 minus R. All these 2-point correlation functions. Huh. That's all it is. You sort of know the form of each one of these. There's no squares in this one, right? There's no G naught R squared. This gives you a G naught R squared here, right? But in this case, you just connected every external vertex to every internal one. So this is great if you know the form of that 2-point correlator. But generally, you don't know the R dependence. Or if you know the R dependence, you have to do what we did a couple of classes ago. And you have to Fourier transform into momentum space, right? Write the thing in terms of, A inverse, if you want to call it that. And then get the momentum space form, then transform back into real space. So it's actually easier to calculate things directly in momentum space. It's just, I mean, it's just a matter of basically translating what these diagrams mean into momentum space. Or so right now we're labeling, you know, the full d plus one dimensional coordinate. But we could also do everything in momentum space. So let me just say something about that. Now, I'm not going to make you do any of these calculations, so don't worry too much. Basically, what I want to do is just give you a flavor for, you know, what these things mean if you see them somewhere. And I guess sort of the effort that goes into calculating these higher order contributions to these interacting correlation functions. So people go to higher orders. They label these diagrams by like the number of loops in them or something like that. This might be a one loop calculation. Then you'll hear people talk about 2 loop calculations and 3 loop calculations. Those are calculations that are going to higher and higher order in U. And you can basically make a career off doing that, you know, adding higher and higher order corrections. And sometimes those corrections are very important. They actually change the whole sort of dynamic or the whole physical interpretation of the theories. Actually, Sungsik's famous for this. He's done very high order calculations in some field theories and shown that it's not just somehow a perturbative correction that keeps getting better. Higher order diagrams can actually change the physics of some of this stuff. So as you can see, it gets pretty tricky as you go to higher and higher order. You have to get all these combinatorial things correct. What happens in momentum space is you actually eliminate some repetition of these diagrams, and you're also dealing with the proper or the known functional form for your Green's functions quite often. So momentum space things can be easier. Forget this 4-point correlation function. Okay, this thing that we're calculating, I don't know. I mean, you look at some of these diagrams. This one looks a lot like this one. It just has another loop in it. Do I really have to treat that one completely separately? You know, as you go to higher and higher orders, you'll repeat diagrams like this. You'll repeat diagrams like this that just have extra loops in them and so on. And some of that repetition can be fixed in momentum space. For example, we know that Gaussian 2-point correlation function in momentum space. Let's just look at that one first. Just remember what we're calculating. That's this thing here. The first diagram, the 0th order contribution, is just this 2-point correlation function. And we've labeled the external, if you will, vertices by R1 and R2. Right? Now, you know, we can write the action in real space. Do I want to? I'm not sure I want to. Yeah, okay. So we can write the action. So it's like the Gaussian action in real space. I remember why I don't use R now. It's because this is a different R. Square root M. Just, this is square root of the mass. Just remember that's different than this R. I was using X before. I wondered why I switched to X, but it's too late. So remember, all we need to do is basically invert, take the inverse of this term, but we can't do it in real space because we're written in terms of basically the derivative operator in these fields, right? So we do it in terms of momentum space. I think I only did it in 1D before. And I think I normalized things wrong. But in higher dimensions, all you're doing is replacing every instance of that field with the Fourier transform. It's always good to remember how your Fourier transforms work. Integrate over R. I have two of these fields, so I have two P momenta. And I'll call them P1 and P2. And all these two pi's make sense in between your definition of the normalization of the Fourier transform and your definition of the Dirac delta function. Right? Remember, we have like a derivative that acts on the exponential that brings down a p squared. We have our two phi's now, which are in momentum space. That's incredibly messy. That's just a d-dimensional generalization of what we did in 1D. Okay, this is the important piece here. And then we have an integral over R, right, which gives us a delta function. And it makes P1 plus P2 equals 0, which is important in a minute. Okay. Because these delta functions define the momentum conservation laws. I wrote Q by accident. So in general dimensions, P's. So that delta function basically follows around for the whole calculation. And what it does for S naught, phi p, phi minus p. I forget what order they occur in. They commute anyway. P squared plus root of the mass. Oh, yeah, wrote too many fields. Right, and once you have things written like that, then 1 over this thing is just your Green's function momentum space, okay? So it's the same in higher dimensions. And I don't remember if I was labeling the Gaussian expectation value before. So we know that. So we know what this is in all dimensions. Right? We'd like to do our diagrams in terms of basically, a diagram that was labeled with P1 and P2, where this thing is just G naught, P1, P2. Or G naught P with all the constraints put in. And a delta function, which is like the conservation momentum, which gave us this minus P, basically says that we can label this thing with just a P, but it has to be P for this, P for minus this, minus P for this, sorry. You can just put an arrow on that thing. So the conservation momentum is just encoded by that minus sign, if you will, is just encoded by the direction of that arrow. So a momentum space diagram will look very similar to a real space diagram, except the conservation momentum is going to be built in. So we're going to have to label all these things with arrows. Okay, so that's just the Gaussian part. It's very simple there. So when we do the phi-4 part of the action, we just have to keep doing these Fourier transforms. Okay? And when you do Fourier transforms, you just got to keep track of all these delta functions that come out from the definition of the delta function, basically. Okay, I'll just basically write down what happens for phi-4 terms. I'll let you do all the Fourier transforms yourself. It's no more interesting than what I just did there. But you have lots of different diagrams. So, the interacting part is going to have, I started using Q in my notes, but I don't want to. But I'm going to accidentally write Q's all the time now. All right, we're using Q's. It's going to have 4 of those momentum integrals. I don't know what I did here. P equals P. That's terrible, eh? And then you're going to have the phi-4 terms. One, two, three, 4. Okay, so this is going to be like the thing that comes in your Dirac delta function to give you conservation momentum. So higher order terms will have just more complicated conservation laws. Those conservation laws come from doing this integral. So there's some 2 pi's and a delta function. So what you have to do is basically constrain the arrows on these higher order vertices to take into account that delta function, that type of delta function that has all these different terms in it. Okay, so I'm not doing a full derivation. I'm just showing you the gist of how this momentum space calculation looks like. So from this delta function, momentum will be conserved at the internal or interaction vertices. Of your diagrams. So for example, you can label these, so every diagram that has 4 lines coming into it, you label them Q1, Q2, Q3, Q4. And then you can draw directions, arrows on these things, but you have to be subject to that constraint. That's what conservation of momentum is. Let me just do one. I'll just sketch how this one's done. So you had a diagram that was like this. And the 2-point correlation function to order u squared was labeled R1, R2, and then the internal interaction vertex was R. Depending on what you take that diagram to mean, sometimes I write the integrals and stuff inside the diagram, sometimes I forget. So I have an internal vertex that has a line connecting itself, so it's R minus R. Then I have, let's see, R1 minus R, and R minus R2. That's for this line and this line. And I've integrated over R. Well, that's the thing we call G naught 0. Right? There's no dependence. That internal line that self-connects, there's no dependence on the integral. So you'll get something like, so it's going to be minus u over 2. The trick to doing these Fourier transforms, which I won't do, is to recognize that this function here has no R dependence in it. You're actually integrating out all the R dependence with this integral. So you can do this proof with defining a convolutional function. Just something like G star G, R1 minus R2, no R dependence. But I'm not going to do the full Fourier transform, so. I mean, you can just literally plug in all the definitions of the field transformations in Fourier space. Okay, so once you do that, maybe skip ahead. Ooh. So if I do a Fourier transform of that thing, which in my shorthand notation, G star G, functional dependence, R1 minus R2, you will get because you don't have enough to do as an exercise, you should get a delta function for Q1 plus Q2 and the momentum space for one of the Q's, one of the momentum squared. Try it. Plug in the 5R expression and change all your P's to Q's, and then you'll get something like this out. So you'll have a delta function. And I think it's instructive to see where this comes from because this is your conservation momentum. But so this thing written in Fourier space, this single diagram written in Fourier space, so you have the U term. This thing's written in terms of coordinate space, right? But if you just integrate it out, I mean, you can write that coordinate space as a integrated out momentum space too. So you can write this full thing in momentum space. Just made a bunch of these 2 pi d's hanging around. This delta function. How am I labeling these delta functions? They should be d-dimensional delta functions, right? I'll trust you'll remember that. What do I have? I'm missing a u over 2. This term's already written in Q space. And this thing here, which is written in real space, is just a d-dimensional Fourier transform of the Q space 1, which we already know. So why not write it like that? Because we want to write everything in terms of, like this bad boy here. So if you look at our diagram, we could define a momentum space diagram. Which would be something like, those will get boring after a while, carrying those around. Kind of like a constraint on a diagram that's labeled by Q's. All right, so I have an internal Q, a momentum, and a momentum. I'm going to write this up here, Q1 and Q2. And I could just take this constraint into account and write this diagram somehow like that. Okay, just saying the momentum coming out of Q1 has to be the opposite sign of that going into Q2. It's actually too simple, sort of. So the general rules of transforming between, real space diagrams and momentum space diagrams follow this basic idea without deriving them. So basically, write the diagram down. You draw arrows on every line. Enforce total momentum into internal vertices is 0. And then integrate over all the free momenta. That's this bad boy here. Integrate over all free. I'll say internal. That's just a set of rules that I haven't defined, but they're obeyed by that simple diagram. And the advantage of knowing these rules is when you go to more complicated diagrams, you can just perform the momentum space calculation really quickly. So instead of, I won't do the explicit calculation because I've already bailed on that. So just let me just show you what a more complicated diagram looks like. So a second order contribution to a 4-point correlation function. Things are getting complicated when you're talking about something like this. You have 4 R1, R2, R3, R4. I think I did it like this before. All right, that's the 4 fields from your 4-point correlation function. But in second order, you have 2 internal vertices, right? So you do all this thing where you connect these things all with their combinatorial factors. So let me just pick one. Well, one of them is not a vacuum graph. How about that? So say I figure out all the combinatorial factors. I have to calculate how this one contributes to my overall 4-point correlation function to second order. You know what the integral expression is? You could write it down, do the full Fourier transform, and then write it in terms of things that you know. But you'll see that it just follows these basic rules here. So assign momenta to a particular direction for each line. So let me just label, oh, I remember why I use Q's now. People use P's for the internal momenta and Q's for the external. And you know which ones you're going to integrate over. Those are all momenta. I can assign directions to them. Let me go this way. And in here. And I can write the integral expression for this thing. Okay, so it's like, I do the combinatorics, I get the diagrams, I start labeling them with momenta, and then I essentially can just, from the rules, pick the integral expression that I need and have this thing written in terms of what I want in just a few easy steps. So that's 1, enforce the total momenta and internal vertices to be 0. I use that with delta functions. And then I have to just add the integrals for all the free internal momenta, which is those P's now. So that thing will have an integral expression, a bit right proportional, because I probably dropped a ton of things. This is a u squared term. So I'm going to have G naughts for all the Q's coming in, Q1, Q2, Q3, Q4. The P's also, but I have to have an integral for each one of them. P2 and P4, I call them. So I have the G, P2, G, P4. I haven't done step 2 yet. I've done step 3. I have to enforce the total momentum is 0 going into those interaction vertices. That'll give me delta functions like, there's 2 vertices, so I should have 2 delta functions. D-dimensional delta function. So the way I have those arrows, it's going to be, if they're going in, they get plus signs. P2, sorry. Q1, Q2, P2, P4. These all have 2 pi to the d's probably. And then I have another vertex, Q2, Q4. Oh, I got my labels wrong. This should be 3. Q2, Q4. But now I have to minus P2 minus P4. That's it. I mean, of course, when you're sloppy, you make a bunch of mistakes and it screws everything up. But the delta functions just give you constraints. So let's see. You can just take one of the delta functions and say, this one's giving me, I guess I'll say P4. You know, so solve the constraint in terms of P4. Q2 plus Q4. Yeah, minus P2. And then that first delta function, if I put in P4 here, will give you Q1 plus Q2 plus Q3 plus Q4. Okay? So it means you can label I'll just write the diagram as the last step. This has probably ceased to be enlightening. Two pi to the d's, I'm going to drop those. And I can simplify my momentum integrals. I'll only have I'll say the 2, P2. As long as I write my P4 is Q2 plus Q4 minus P2. And then this one is Q2 plus. Okay, well, when I was in grad school and I started seeing stuff like that, I went into numerical physics. Because, I mean, that's what these perturbation calculations are, okay? You go through this all once, you figure out basically what this means, you figure out where it comes from with the Fourier transforms, and then for all these higher order diagrams, you write down the diagrams, you take all the constraints into account, so you don't have a bunch of redundant momenta, right? Because the delta functions make it so you have constraints between all your momenta. And then this is the thing that you have to, you know this in momentum space, so this is the thing that you're calculating in the end. And that's giving you these perturbation theory corrections. I'm not going to make you do it, because I hated doing it. That's all we're going to say about perturbation theory. What's going to be more useful in your lives? Any questions on this, by the way? I hope that gave you a flavor for what goes on in these calculations, but I think we're doing more fun things on the assignments. So. Actual second quantization calculations, computational things. Let's see.
Can I get one for Carrie?
Yeah, this is online too. Let's just talk about this real quick. Yeah, I figured you watch me do this for an hour and a half. You don't need any more practice. So we're going to do practice solving many-body systems, doing computational things. And this is, I think, actually something that's really useful, that's going to come out of this class. So we've looked at the Ising model several times. You've done an exact calculation, done a Jordan-Wigner transformation. You know where the critical point is. We've talked a little bit about one-dimensional correlation functions. You know what to expect there. We're going to put some of this stuff together now in the computationalist project. This thing's due, right? Like I need this, basically, I need to be able to mark this by the time the end of semester comes around and the registrar requires my marks. So I think if you get it to me by April 12th, which is like 2 weeks, isn't it, after the last assignment's due? It's like a month and a half from now, right? Yeah, so it seems like a long ways away, but it's not. So you're going to hand in the last assignment. You're basically going to have a couple weeks. But you should get started at least on question 1, I think. So just, you have another 2 weeks to do your assignment 4. But when you're bored, alone at home on a Friday night, just start with question 1. And if you have problems with question 1, let's nip that in the bud before the end of semester, before the last 2 weeks where you're scrambling. So there's a Python code for this. You're using Python. Who's used Python before? All right. It'll be easy for you guys. If you haven't used Python, I suggest you download this Canopy. I think it's called nthought Canopy. I don't know, just Google this. It's a Python distribution that should have all the libraries and everything that you need. It'll have all these diagonalization routines and so on. You can actually do all your plotting. So, I want a proper project. I want you to write things out, tech it, or put it on a wiki or whatever you want. But this is a nice plotting library called matplotlib. So you can, in principle, do all your calculations in Python, and then you can do all your plotting, all your analysis, all your fits and everything like that also in Python. Although you don't have to. You can just produce data and then use something else. But I think it's worth kind of learning matplotlib if it's something you think you might use in the future. I can give you more information on this if you need it. So once you download Python, I have a program to get you started on the Dropbox. I forget what it's called, but it's basically the transverse field Ising model in 1D with open boundary conditions. If you run that thing, what it does is it builds a Hamiltonian. So it actually builds a Hilbert space. And then from that Hilbert space, it builds a Hamiltonian, which is like the hard part. So I've done the hard part for you. When you do diagonalizations, which is all this computational project is basically building Hamiltonians and diagonalizing them. You're going to see all sorts of crazy stuff. For one thing, it's going to show you what the fundamental restriction is on these many-body quantum systems doing things exactly, right? And it's kind of a trade-off between, in this perturbation theory, you're in some continuum, but what you're doing is you're adding these things perturbatively, and at some point they're getting so complicated that you quit. In computational approaches, you're not adding anything perturbatively. Every interaction is handled exactly, but it's the finite size that kills you. So it's like the exponential Hilbert space that kills you. So in the first part of the assignment, you're going to build a full Hilbert space. And I've done this in some way that uses bitwise operations. So you can imagine that you're working the sigma z basis. And for a many-body system of n spins, you're just storing state vectors that look something like that. So what the piece of code does that I gave you is it translates this thing into zeros and ones. And then it turns that into an integer with bitwise operations, which I should know how to do, but I'm not going to embarrass myself in real time. So this is some integer. And all I do is I loop over that integer in real, in a loop. And that loop has the size of the full Hilbert space to the n. Okay, so once you have that Hilbert space built, what you can do is you can just build a Hamiltonian through its matrix elements. So you can have, this might be alpha prime, I don't know. And the trick with diagonalizations is not to do a double loop. I already have one loop that's going over all the kets, say, or all the bras, doesn't matter which one you think of it as. And in order to build a Hamiltonian matrix element, you need another loop, right? You want to loop over alphas and alpha primes. So this will basically kill you right away. So the way that I've done things is basically by calculating, the alpha say by operating with the Hamiltonian on that ket. So you're looping over something that looks like that. You have to have your Hamiltonian encoded in a way that it knows what that is. And then as part of that loop, you also produce the alpha. So it's easy when things are diagonal. In the transverse field Ising model, you have a diagonal term that's sigma z, sigma z. That's easy because your bra is equal to your ket. But when you have the sigma x term, which you should write like that, you have to imagine that, you have to look at the Hamiltonian and imagine that you're basically operating on this thing, maybe flipping a spin, and then turning that into your alpha. So that's what the code that I've given you has done. So it's starting you out already with this way of building a Hamiltonian, building Hilbert space and building a Hamiltonian. So correspondingly, your assignment starts easy. Exactly diagonalize the Hamiltonian. Done. Oh, for periodic boundaries, not done. So you have to add a bond. And you're calculating the energy per spin, which is something that's already coming out of the... So what happens is, once you build a Hamiltonian, in that code, it's just passed to an eigen solver. Okay? Just a full diagonalization. You get the entire spectrum of the Hamiltonian. So question one is just playing with this. Look at the ground state, look at the low-lying energy states. You have the eigenvalues, and you have the eigen vectors.
You say do it for as large n as your computer can reasonably handle.
Yeah.
That's a reasonable value so that we don't break your computer.
Go ahead and break your computers. It's fun. That's how you learn.
The thing is that I don't want to wait for 5 days until...
No, your memory will crap out first. Okay. So when you're doing this, you'll be building the Hamiltonian, and you'll fill your entire memory and crash your computer. So we're talking like 12 or something like that. Or maybe 14, I don't know. I forget. I think you can't fit 16 sites. I think you need 4 gigs to fit 16 sites, maybe. You can calculate it. Just calculate the size of the Hilbert space, right? And imagine you're using floating point or double precision or something like that. You should be able to get an estimate for the Hamiltonian, which is like 2 to the n by 2 to the n. And that's what you're literally storing. And so you'll just explode your memory right away. You know, so save all your Word documents before you do this, but you'll figure it out. And at some point it'll take some time, but I mean, that's, you know, it's going to take a few minutes or something like that for these sizes that you can handle in the memory. So then for whatever that size is, basically I just want you to calculate energies, correlation functions, blah, blah, blah. And in part C, you know, it's like you're looking at, you're going to try to fit the real space correlation function to extract the correlation length and so on. You'll see how hard this is with diagonalization. So you should know you know, we talked about basically the analytical forms. So you're basically checking these against your diagonalization. In question 2, you're not going to build the full Hamiltonian. We're going to do a smarter thing called a Landshos diagonalization. So it involves, instead of looping over this entire basis state, now you're still looping over the entire basis state. What you're doing is storing the Hamiltonian sparse matrix form. And you're using iterative diagonalization on that sparse matrix. So instead of the 2n by 2n Hamiltonian, this thing should be way smaller. Okay, so that's basically question 2. Question 3, I've changed the symmetry of the Hamiltonian. So instead of being the transverse field Ising model, which has this term, it's the XXZ model, which has a term that's like S plus, S minus, plus S minus, S plus. That's the XY term. The significance of that is that it conserves the SZ value. Okay, so like when I use an off-diagonal operator here, I flip that 1 to a 0. Remember? But if I use the off-diagonal operator in the XXZ Hamiltonian, I have to flip a pair of these things. It's plus minus, plus minus, plus, right? So I would end up just exchanging the two values of those spins. That means you can restrict your diagonalization to just a subsector. So your Hamiltonian is block diagonal, with each one of those blocks being the SZ value, the total SZ value, if you add all these things up. So all of a sudden your Hilbert space becomes smaller. You're using a Landshos diagonalization. And so between that symmetry and the sparse matrix, you should be able to add like a couple more sites. So you're going to look at the same things. You're going to look to see if you can identify, I guess, just ground state energies and so on. And then in part 4, I'm going to have you calculate the entanglement entropy. Okay, so that involves knowing how your basis state looks. And it involves knowing how to divide up, you know, sites into 2 spatial regions, which we call A and B. And, I mean, if you get to that question, come see me. But I'm going to talk about entanglement entropy a little bit more in lectures near the end of class in the last couple of weeks. So I'll talk more specifically about question 4 when we get to it. So like I would say, start into question 1 and just see if you can get Python running, see if you can build that Hilbert space, diagonalize that Hamiltonian, and so on. And I'll talk more about this as we progress in this last few, weeks of class. Okay, that's it. See you guys Thursday.